Regular expression gain widespread adoption in network security, network monitoring application, and applications that deal with a huge database. Their widespread use due to their expressive power and flexibility for describing useful patterns. Due to some problem in network and security that requires packet processing, which is searching packet content for specified pattern, which are typically specified as regular expressions. An efficient index structure for regular expression presented the regular expression tree, which is a novel index structure for a performing fast retrieval of regular expression that match a given input string. In order to overcome the challenge of indexing the infinite regular set with no well-defined notion of spatial locality, they developed a novel measure for comparing the relative size of infinite regular language. They also proposed the innovative solution for the various regular expression tree operation. Finally, they showed how sampling-based approximation algorithm can be used to significantly speed up the performance of regular expression tree operation. Their experimental result with synthetic data set clearly demonstrate that the regular expression tree index is significantly more effective than performing a sequential search for matching regular expression. Suppose we want to generalize the three automata for the regular expression A, B, B star, A, C, C star, and A, A star B. The DFA for the union of the three automata is depicted in figure 7a. Suppose A equals 3, that is, we would like the final generalized automaton to contain at most 3 stated. We trace the step of algorithm generalize FA on the union automata M1. The first pair of states merged by the algorithm are stated 3 and 6, since the language for the resulting automaton M2 in figure 7b is AA star, BB star, or ACC star, which is smaller than the resulting language when other pair of states are merged. For instance, merging states 3 and 4 result in the language A, B or C, B or C star, or AA star B, while AA star, BB star, or CC star is the language when state 2 and 5 are merged. In the next iteration, state 2 and 5 are merged to yield automaton M3 in the figure 7c, whose language is AA star, BB star, or CC star. And in the final iteration, state 1 and 2 are merged, and the final automaton M4 in figure 7d containing 3 states is retained by algorithm LM4 is A star, BB star, or CC star. The result shown as follows. In figure 8 shows the performance result as alpha is varied. The graphs indicate the regular expression tree outperformed the sequential file approach by up to a factor of 3 and 2 respectively for the number of automaton comparison and search time. Their results indicate that both the number of automaton comparisons shown in figure 8a and running time in figure 8b improve the larger value of alpha. This is because as alpha increases, the precision of the bounding automata generally becomes higher, thereby resulting in better burning of force drops, and hence fewer number of automaton comparison and index page access. In figure 9 shows the performance result as probably is varied, since the similarity of the regular expression in each cluster becomes higher with a larger value of probability. The regular expression tree approach is able to improve its filtering, thereby resulting in less force drop and hence improve query evaluation. Therefore, the performance of regular expression trees improve as the probability increases. In figure 10 illustrate the performance result as size of data is varied. We note that the performance gain of regular expression tree increase with a large value of size of data.
As we mentioned in our survey, that regular expression gain widespread adoption for packet content scanning, which is crucial to network security and network monitoring application. And there are regular expression patterns which are used in packet content scanning. Some of these patterns create complex DFA, which cause large size of DFA. And fast regular expression matching usually implement by NFA approach, because the FA implementation can have growing in memory. The author produce rewriting technique make the memory efficient DFA based approach are possible. As I said before, there are some patterns create complex DFA. There are two cases of this pattern. Patterns start with the circumflex and contains classes of character with length restriction. Create DFA has a quadratic number of state. And the second case, patterns start with a star and having length restriction, generate exponential number of state. To reduce memory usage in DFA, when you use this type of pattern, the author produced two rules of this pattern. This type of pattern that start with the circumflex can be written this way with equivalent guaranteed under the condition of non-overlapping matching. And this new pattern generate a DFA of linear size. The second rule, this rule first enumerate all cases that don't satisfy the pattern, and then attach the original pattern to the end of the new pattern. In our word, star is replaced with cases that don't match the pattern. And this rule generate linear number of state in the DFA. This table shows how these rules make significant memory saving when they apply them, and the DFA size reduction rate is over 98%.
My paper topic is high-speed regular expression matching engine using multi-character NFA. The authors of this paper propose a novel logic design method using multi-character NFAs to realize high-speed regular expression matching. The method accepts several regular expressions as input and outputs a description of the corresponding NFAs in HDL. NFA construction is conversion of the tree into an NFA structure and modification of the NFA to support multiple characters per clock cycle. It consists of two tasks. Phase 1, conversion of a regular expression in post order into its NFA graph that processes a single character every clock cycle. And these are some examples of NFA graph in phase 1. Phase 2 is conversion of the one character NFA graph that comes from phase 1 into an NFA graph that can process 2 to k characters for desired natural number k every clock cycle. And these are some examples of two character NFA graphs. HDL generation is specification of the multi-character NFA using structural HDL. The authors implement their ideas as a software tool named Regular Expression to Verilog NFA Translator. Its input, one or more regular expressions, are converted into one character NFAs, which are then converted into multi-character NFAs, which is the output specified in Verilog HDL. The authors do performance evaluation, and the results of that show that their method can significantly improve throughput at only a relatively modest cost in terms of additional logic, even without turning on optimizations while performing FPGA mapping. By turning on some of them, logic speed is likely to increase. Therefore, further throughput improvement can be expected. In conclusion, regular expressions are quickly becoming an integral part of language specifications for several important application scenarios, such as network security, network monitoring, HTTP load balancing. That is due to their expressive power. Also, many of these applications have to manage huge databases of regular expression specifications and need to provide an effective matching mechanism that quickly identifies the regular expressions in the database that match it.